Here we have lesson number 6 in Unit 6. This is about geologic dating practices. So the first thing that we need to talk about with geologic dating practices is called Uniformitarianism. And this is the basic principle that the geologic processes that are going on today are the same ones that have occurred throughout Earth's history. So everything we've talked about with like the way that volcanoes erupt and the way that the rock cycle works, weathering and erosion, compaction and cementation of rocks into sedimentary rocks. These things have all been going on since the Earth was first formed, and they're all still going on today. So everything that was happening previously is still happening today. So we have two main types of geologic dating practices. First, we'll talk about what's called relative dating. Relative dating tells what order things happened in, but it can't tell their exact age. So we can tell like if one rock or fossil is older than another one, but we can't tell how many years old it is. So there's several different laws that we pay attention to when we're using relative dating. The first is called the law of superposition, and this means that in undisturbed rocks, so nothing has happened to churn up these layers, the layers at the bottom formed before the layers at the top. So the oldest stuff is at the bottom, the youngest is at the top. This works, you can relatively date fossils. So for example, this pointy shell fossil is older than this snail type shell fossil here because it's found in a layer deeper than the snail fossil. The next law that we use for relative dating is called the law of original horizontality, and this means that layers of sediment are deposited in flat horizontal layers, and any kind of tilting or folding that happened to them happened after they were deposited. So these layers were originally flat, something happened that pushed them upward well after they had formed. Next, we have what's called the principle of cross-cutting relationships. So this means that anything like a fault or an igneous inclusion that cuts through another rock is younger than the rock they cut through because they couldn't cut through them if that rock wasn't already there when they formed. So inclusions are just any kind of rock unit that's contained within another rock unit. Typically, they're going to be igneous rocks because magma will kind of inject itself upward through other rocks that are already there. Examples of these we've talked about before are sills, dikes, and batholiths. In this picture here, we can use the law of superposition to tell that this layer is the oldest layer, this layer is younger than this one, and then this is an igneous dike because it cuts across the layers. This is the youngest layer because it cuts through the other layers. So next we have what are called unconformities, and these are just visible breaks in the rock record. So first we have what's called an angular unconformity, and this is when you have young sedimentary rocks that have formed over older layers that have been tilted or folded in some way. So you can see that these are old layers, they got pushed up and tilted somehow. This squiggly line here is the boundary, the angular unconformity, because now we've got flat undisturbed layers above these ones. So you can see there's an angle formed between the flat layers and the tilted layers. So the next type of unconformity is called a disconformity, and this is when there's some type of visible erosional surface between sedimentary layers. So you can see here, we could say this is some type of maybe sandstone. You can see this layer here, there was erosion that occurred that broke away some of this sandstone here before this, we'll call this shale, formed on top of it. So this layer right here where erosion was occurring, this is called a disconformity. The next type of unconformity is called a nonconformity, and this is the boundary between an igneous or metamorphic rock layer and sedimentary rocks above. So you can see right here, this green rock here is some type of igneous intrusion, maybe it's a batholith of some sort, and then you have got sedimentary rock layers formed above that. So we can tell that these layers were here already when this igneous inclusion occurred because it cuts through them. So that's the principle of cross-cutting relationships right there with this nonconformity. We can also use correlating rock layers when doing relative dating because if we know how old a certain type of rock is, if we find that exact same type of rock somewhere else on Earth, then we know that that rock is the same age and that was formed at the same time even though they're not in the same place. So the other major type of dating practice is called absolute dating, and this is when we can get the actual age in years of a rock or a fossil or something. So while relative dating, we could just tell what was older or younger than something else. With absolute dating, we can actually tell exactly how many years old something is. So absolute dating employs known rates of radioactive decay. So this occurs when you have some type of unstable radioactive parent isotope, which is just some type of element that has too many neutrons crammed in its nucleus and makes it kind of unstable. And over time, those unstable isotopes will decay into a more stable version called a daughter isotope. And so what we can do is we can look at the ratio between how much parent isotope there is in a certain rock or fossil and how much daughter isotope there is in that rock or fossil, and we can approximate how old in years that rock or fossil is, because this radioactive decay happens at a known rate for different types of isotopes. So the main way that we use this radioactive decay is by looking at the half-life of the radioactive elements. So half-life is the amount of time it takes for 50% of that amount of radioactive element to decay in the rock or fossil or whatever the thing is that we're doing absolute dating on. So you can say if you had, let's look at this chart here. These are really common isotopes used in radiometric dating. You can say, well, carbon-14 decays into nitrogen-14. It takes 5,700 years. So something you could say for a fossil, something that's alive right now, if it has 100 grams of carbon-14, and then we go look at a fossil and it has 50 grams of carbon-14 and 50 grams of nitrogen-14, well, that means half of that carbon-14 has decayed while that thing has been dead, which means that one half-life worth of time has passed, which means that that fossil is about 5,700 years old. So the reason that there's a star next to carbon-14 here is because that is the only one of these isotopes that we can use to date things that used to be alive. So it's really useful for dating fossils and artifacts and things like that. But the only catch is that it's only good up until things are about 100,000 years old, and then at that point there's not enough of the carbon-14 to be able to tell how much there is anymore. And so that is the limitation of carbon dating.